Hello everyone, welcome to the class ECE418, the Statistical Signal Processing. Today the class for the Wednesday of the first week. We will do some review on some early knowledge about signal processing, about the linear shift invariant systems. Alright, it is a part of here in the textbook. This is section 2.2 of the textbook. This is this part. Okay, now let's go over the detail about it. This is ECE418, the lecture for first week Wednesday's class, and it will cover section 2.2. Section 2.2 is kind of a review of signal processing. Of course, this is just for some early things. This course now is also signal processing, but this is a review of some early things. The most basic thing is RSI system. RSI systems. What is the RSI system? Here, error means linear. Suppose the system like this. System, I use T, capital T for the name of the system. Right. Then linear means T with input is A times a signal X of N, will equal to A times T of X of N. Now you can move A out. So here's you use A times X as the input. This side use X as input. So here's the output we input with the input AX, and here's the output of the system with the input is X, then times A. So here you input is X, and then you take the output times A on the output. This one you get the output directly, but the input is A times X. Okay, these two results are the same. And the second thing is, if you have two signals as the input, here means summation. If you add two signals together as the input, then this will equal to the output when input is the first signal plus the output when the input is the second signal. Alright, so this means linear. And SI means shift invariant. Shift invariant. Sometimes people maybe call it as TI, the time invariant, the same meaning. Alright, so what it is, that means you have a signal N and shifted by a signal X of N, and shifted by ND, some kind of time delay. You use this as input to system, will equal to, okay, there will be a shift, I say to Y of N minus ND, where Y is the output of the system where input is X, like this, right? You use X input, you have a Y as the output. Then this Y you shift by ND, you get this signal. And this side you use a shifted X as the input, you get an output. Okay, these two signals, they are same. So this is a shift invariant. Alright. So LTI means a system has both features. It is linear as well as shift invariant. Then how to describe RSI system? Description of RSI system. So the basic thing is difference equation. See, difference equation. It is usually it looks like this. It is a summation of some terms. I say the coefficients are k times y of n minus k, and k run from 0 to some other, like suppose it is p, okay, and equal to some other terms on x, on input, some bk times x of n minus k. Here k run from 0 to some q, okay, p and q that are others. Yeah, so usually this equation looks like this. The p might be different, a and b are different, and you have different systems. The difference equation. So basically, any RSI system can be written by a difference equation. Okay, this is the basically. And then we can have some other way to describe the system, which can provide something, make it easy, make it simple to work on it. So the first one is a impulse response. Impulse response. People also call it as a unit symbol response. H of n. What is H of n? The output of the system when the input is third of n, which is we call it a unit symbol signal or unit impulse signal. It looks like this. Third of n is defined as its value will be 1 or 0 depending on n. If n is 0, it's 1. If n is not 0, third is 0. As a graph, you can see this is n. When n is 0, its value is 1. When n equal to some other values, right, you get 0. You get 0. Looks like this. So you have a sequence of 0, but here when n is 0, you have a parse key. You can say you have a unit symbol, a unit parse or unit symbol. So you call it an impulse response. Right? This is the impulse response to the impulse, or the response to the unit symbol. Right? Same thing. So this is a impulse response. Impulse response. For the impulse response, we have a very good feature. I'm writing here. If x of n is the output, is the input, then the output is y of n, which equal to h of n convolution with x of n. This one is a convolution. Convolution of two signals. It is defined as this one. It's a summation of h of k times x of n minus k. K run from negative to positive infinity. So that means, if h of n is given, then no matter what is the output, you can always find no matter what is the input, you can always find the output by this formula. Okay, this is one thing. And for how to calculate this convolution, you should know how to do it, right? Yeah. Okay. Then we consider the second thing. impulse response. Okay, and the description. I say this is 1, this is A, this is B. Now we have C. It's a frequency response. Frequency response h of e to the j omega equal to dtft of h of n. So this is frequency response. Okay, here dtft refer to the discrete time Fourier transform. And Fourier transform. We need a Fourier transform to find the frequency response. The definition is like this. For any signal, like I said, some omega of n by dtft, we will have capital omega of e to the j omega, which is a summation of all these omega n, right? Omega n is here, omega n, but each one times exponential power negative e to the negative j omega n. Here n run from negative to positive infinite summation for n. Yeah, just like this. So dtft, by definition, you can calculate by this way. And of course, in most cases, you calculate it directly from the definition. It's a long work, costs a lot of time, right? And people used to use tables. In the table, there are some result, useful result. Someone else already calculate and find those results, and those results were posted in the table, so you can use the result in the table. Yeah. Okay, so this is the frequency response. For frequency response, we also have a similar formula, looks like this, which is y of e to the j omega equal to h of e to the j omega times x of e to the j omega. Now we have this one. By this one, you can find the output if input is given, but we need to work in the frequency domain. We start from, like, you have x of n, you perform dtft on x of n, you get a capital X of e to j omega. Then you this one times the frequency response. This is frequency response. You times on it, then you get y of e to the j omega, and then you do inverse dtft. Then you will have y of n. Okay, so you can get y of n based on the frequency response. And for frequency response, we also have a very special case. If input x of lowercase x of n equal to a cosine of omega naught n plus some alpha, or exponential power to the j times omega naught n plus alpha. We have this case or this case. You can also put a sign here, but the sign you just change some shift by pi over 2, right? You can go back to cosine. So we just consider these two cases. They are sinusoid. One is in for real numbers. This one is for convex number, right? So they are sinusoid. If input is a sinusoid, then the output, this is output, y of n will equal to h of e to the j omega naught times input is cosine omega naught n just plus alpha, right? This is the original one. and then I need a plus phase h of e to the j omega 0, phase angle of capital H. Oh, here I need a magnitude. Alright, this is y of n. If cosine of omega 0 n plus alpha is the input, and the output will be just this one. And if input is this one, it will be h of e to the j omega naught times e to the j omega naught n plus alpha. That's it. So this is for the frequency response. When you have the frequency response, how do you how to find the output for a given input? Generally, you can always use this method. Right? You can also follow this way if the input is a sinusoid, cosine, sine, or combine of sine and cosine complex number way. Okay, this is C, the frequency response, and the D, the transfer function. Transfer function. For transfer function, it is also, we have h of n, then we perform z transform on h of n. Then we have h of z. So both frequency response and impulse response, they're coming from h of n. Both frequency response and transfer function, they're coming from h of n. Just use different transform. Right? Here's a z transform other than for Fourier transform. This is a z transform. For h of z, we have similar thing. We have similar result. Y of z will equal to h of z times x of z. So similar, when you have the input in z domain, you times it with the frequency with the transfer function, then you can have y on z domain. Then you perform inverse z transform, you can have y of n in time domain. Right. So this is the third way. And these three different ways, totally we have four ways. But first way is a kind of a definition. You can think, all the RTI system, RSI system can be written by difference equation. This is basically, usually those equations were coming from some, some real model, physical or electrical, or even like a chemical kind of equation, right? Yeah. And then we can have impulse response, frequency response, and transfer function. And here we need some tools, two of the math tools. The first one is the Fourier transform. The first one is the Fourier transform, and the definition is like this. You have x of n, you perform, okay, here's we will consider dtft, the discrete time Fourier transform. By dtft, you will have capital X e to the j omega, which is defined as a summation n run from negative to positive infinite x of n times e to the negative j omega n. It's like this, dtft. Usually this is, you have infinite terms. So this is a summation with a lot of terms, infinite terms. It's hard to calculate. So in most cases, we use table. When you want to calculate to find this one, you use table. Yeah. And we can go back. This is inverse. dtft inverse, which will give us the relation x of n will equal to some function on this one, some function on this part. Right. What it is a integral Before it, we have a constant 1 over 2 pi. The integral will run from negative pi to positive pi. And inside the integral, we will have the equation x of equation. Here's the x of n, right? This is the x of this one, sorry, capital x of e to the j omega. We put this one here, and times e to the j omega n d omega. Now we have this one. This is dtft. This is dtft. All right. And of course, in most cases, you do not need to calculate these based on these definitions directly. That will cost a lot of time. We use tables. Okay. Yeah. So this is the mass tool for Fourier transform. And the second one is a Z transform. Z transform. For Z transform, similar. I have signal x of n. By Z transform, we have capital X of Z, which is a summation. Now n run from negative to positive infinite. Negative infinite to positive infinite. Okay, here's x of n. Yeah, same as dtft, but then it is the power of z to negative n. Yeah, like this. So here you replace this exponential power e to the j omega, replaced by z to the n. E to the j omega replaced by z. Right? Yeah. So this is z transform. And the Z transform, we can have one thing different way for the transform. That is a region of convergence. Converge. Region of converge. It's RC. Right? RC. We have RC because this, you have infinite terms. If these terms, they are some value larger than 1, then the summation, you cannot have a finite number, right? You want to go to infinite, or you go to some strange places. Yeah, you cannot have a fixed number, right? So we have a range on Z. Only when Z locate inside this RC, this summation, this finite summation will give you this infinite summation will give you a finite value. This is a Z transform. And for the inverse, we also have a formula for the inverse Z transform, but it's out of our course. Yeah, I don't think we have it in our course. We don't need it. But then how to find the inverse Z transform, right? The transform you can calculate by this formula, but the inverse, if you know capital X, can you find the lowercase x? You need help of tables. So this one, we also need tables. All right. So okay. So for the math tools, most important things are these two tables. To transform Z transform or Fourier transform, and each one you have some tables. We can show you where are the tables. First, in the textbook. Yeah, it's some location here. I think Z transform, which is Fourier transform. So page 13, page 12, right? Page 12. But no, not 12. Here's a 5, right? 12 plus 5, so it's 17. Put you here. 17. Oh, it's only 3. 17 is 3, so I need a plus 10 more. 27. Okay. 27. it's here, right? Okay, here's a table. This is one table. We have several tables. This is a Z transform, right? This is DTFT, properties of DTFT. And the second one is here, the properties of Z transform. And third table, this is a this is closed form expansions for some commonly encountered series. When you have series with infinite terms, what will be the result in closed form? Here we have a table with 6 different cases. We need, right? As I told, when you try to calculate a Z transform or Fourier transform, you have to consider a series, a summation of infinite terms. Then how to do the calculation? These formulas may help. Alright, this is third table of chapter 2, and we have more. As here, some use for Z transform pairs. Z transform pairs. So one side is the signal, one side is after the transform, and here we have a region of convergence. Right, so you have these 3. These are for the Z transform. And the DTFT, or DTFT in the front. Actually, I also post some tables in the Blackboard, which is the table I used in different courses. They have more terms than the textbook. The textbook I only give few items in each table. No Fourier transform. Okay. Anyway, Fourier transform and the Z transform, they are almost the same thing. You just replace this Z by the e to the j omega. You can have Fourier transform. Now we can compare. Here, right? This is a DTFT. This is Z transform. Here's the e to the j omega replaced by Z. You get Z transform. So they are just you can say they are similar thing, same thing, or even not even same. This is similar thing, right? Related. So this is Z. This is e to the j omega. Okay. And then the table, that table. That table 2.4. Let me write it down. Table 2.4. Tables 2.1 to 2.4 in textbook. Okay, tables 2.1 until 2.4 in textbook. There will be the page 8, 17, 14, 18, 17, around 17, page 17. Okay, several pages. I just put one here. We have these 4 tables. For table 2.4, replace Z by e to the j omega. You will have DTFT. Alright. Sorry. Here you see Z, right? This is Z. This is Z's. You replace them by e to the j omega. And but we need some condition. Because e to the j omega. They are the complex numbers with length 1, with magnitude 1. So we have some condition to make sure we have the Fourier transform. Let me write down here. But we need a condition. the RC contain the unit circle. Okay, this is the condition. We need this condition. So what is a unit circle, right? I have this one. RC contains the unit circle. What is unit circle? Unit circle equal to all of those z's, the magnitude of z equal to 1, or equal to a plus bj, a squared plus b squared equal to 1. The same thing, right? For complex numbers, they are complex numbers, and they are all of these cosine omega plus j sine omega any real number, but you can restrict the omega run from negative pi to pi. Right, that will be enough. Turn around just 360 degrees, there will be enough. This is not necessary. It could be any omega, right? Any omega, but just this part will be enough. Right? So this is unit circle. Unit circle. This is a real number, a real part. This is the imaginary part for complex numbers, and it is this part. Okay, then what is this? This is just e to the j omega. Omega, any omega, or this one, and both works. Okay, so this is e to the j omega. Unit circle is the set of all of these e to the j omega. This one is a Euler formula. E to the j omega equal to this one is a Euler formula. E to the j omega equal to cosine omega plus j sine omega. This is Euler formula. Euler formula. By definition, this is 1 plus j omega plus 1 over 2 factorial j omega square plus 1 over 3 factorial j omega cube plus and so on. By definition, the exponential power of j omega is defined by this way. This is a infinite series, and Euler proved these two are same. So now we use this. Actually, we use this formula in a lot of places, and this formula we can also have another side, because e to the negative j omega, there will be cosine of negative omega. Negative omega, that will be same with cosine omega, right? Cosine omega, cosine negative omega, they are same. And j sine of negative omega. Negative omega for sine, I can move negative in front. So we have this one. And you do summation of these two, you add them together, the sine terms cancel, you get cosine omega equal to e to the j omega plus e to the negative j omega over 2. And you subtract these two, then cosine terms cancel. You have 2j times sine equal to subtract of them, so you get sine omega equal to this e to the j omega minus e to the negative j omega, and divide by 2j. All of these belong to Euler. Euler's formula. Alright, yeah. And we know, based on these, we know all of these related with all of these. So they are, you put them together, it is just unit circle. And for Fourier transform, we know it's an infinite summation with a constant, the coefficient number coming from the signal times e to the j omega terms, right? The dtft. Where I put it? That's here. Yeah, dtft. You see, you start from signal, you times e to the negative j omega n. You can also think e to the j omega with power negative n, right? This is z. So z is just e to the j omega. Z is e to the j omega, and the e to the j omega is just this unit circle. It's just this unit circle. Now we say we can replace z by this one. Then the requirement is this part, this unit circle. They are useful. They are how to say? They are suitable. You can do calculation, right? When z equal to them, you can have the convergence. So z must belong to the convergence. So the condition is the unit circle belong to the RC, or RC contains the unit circle. So this is the condition. This is condition. Condition for you can replace z by this one to get dtft. To replace z by this e to the j omega, you can get dtft, but you can get only if you satisfy this condition. Alright, now we can look at more. For example, we can check this table. We can have one term, any term, like the third one. Like the third one, I have the third one. Example, a to the n u of n by z transform. I'm copy this one. Okay, you get 1 over 1 minus a z to negative 1, and RC is a z larger than a. Larger than a. I think larger than magnitude of a. Right? Yeah, here should be magnitude, absolute value of r, magnitude of r. The table lost this magnitude. All right. Yeah, that is fine. Right? Should be large. This z is a magnitude, right? So z must be a positive number. If this alpha, for example, you get alpha is a negative one here, then things looks different, right? Something error. You need a magnitude. Okay, I copied it here. Right? This one is coming from the table. Then, if this one contains the unit circle, we have the dtft of a n u of n is 1 over 1 minus a e to the j omega with negative 1. So this is negative. Okay, we have this. And what is this? You see, here's a absolute value of a, and z larger than a. This is RC. This is RC, and the unit circle should be here. This is unit circle, right? Here's 1. This is unit circle. Unit circle should be part of RC, so unit circle cannot be inside. If unit circle inside here, then you do not have Fourier transform. So RC should be here. That means this a is smaller than. So the condition, this one equivalent to a smaller than 1. So we can also state like this: if a smaller than 1, we have dtft of a n u of n equal to 1 over 1 minus a. This is z inverse. Now is e to the negative j omega. So we have this one. We have this one, right? Yeah, and the similar thing. We have several, right? 1, 2, 3, 4, 5. We have 5 signals here. Each one you have a different RC, and you will check. Only when unit circle is a part of RC, you can have Fourier transform with the same formula. Just replace z by e to the j omega. Alright, so this is for the table. You can use this table to get both Fourier transform and z transform. Okay, this is a table in the textbook, and let me see. Here we have what else I want to explain. Now here we have a notation. This is star. We need to use this star later in a lot of places. This notation is for complex number. Complex number. This is a it's hard to say, conjugate. Conjugate of conjugate of a complex number. So a plus bj, this is a complex number. The conjugate, this star means the conjugate. No, sorry, I copied. I need to go to this one. Okay, yeah, this is a conjugate of a complex number. Conjugate of a complex number. That will be you have a complex number a plus bj. The conjugate, this star means conjugate, is equal to a minus bj. You change the sign before j. Yeah, and like e to the aj conjugate, there will be e to the negative aj. Yeah, no matter what kind of complex number, you just change the sign before j. Change the sign before j, you get a conjugate. You get a conjugate. Yeah. All right. The conjugate of complex number, and here you see here is your conjugate, right? In the textbook, you can find some notation in the conjugate. Yeah. Like here, right? Then later we will use them. All right. Okay. So these are for the tables, and how to use the tables to find the Fourier transform or Z transform. And we also find the inverse, right? Inverse Z transform or Fourier transform. Later, when we need to use them, we can discuss them in detail. Actually, I suppose you know that, right? You know this method. And what else I want to give you? Yeah, we have one more thing, just one more thing. Here we have different way to describe the system, right? We have equation, we have impulse response, we have Fourier transform, the frequency response, and by Z transform we have the transfer function. The frequency response, and we have transfer function. Transfer function ABCD. Yeah, sorry, I forgot it. Yeah, so we have several things, right? We have difference equation, then impulse response, then frequency response, which is the DTFT of impulse response, and we have Fourier transform of the by perform Fourier transform on the this is the transfer function, which is the Z transform of impulse response. Right, this is definition, and we have a shortcut to get frequency response and impulse response. This is from difference equation to transfer function. The thing like that. The difference equation, it will be summation of some terms ak times y of n minus k run from 0 to some p, equal to summation of terms bk times x of n minus k, and k run from 0 to q. Here x is the input and y is the output. Then we have transfer function h of z. You can write it directly. You don't need to perform the Z transform. You can perform Z transform. The result will be same. You see, here's the numerator part. Numerator part is just coming from those x terms. Here's a summation of k run from 0 to q, bk totally coming from these terms. But replace x of n minus k by z to negative k. You can say you replace this by z the negative k, right? Z to negative k. That's it. And the denominator, you do the same thing, but based on the output side. So this is summation of k run from 0 to p. This is ak, and this is z to negative k. Right? You replace this part by z to negative k. Okay, then you have the transfer function. You can get the transfer function directly from the equations, and of course you can perform the inverse way. If you know the transfer function, then can you give an equation for the system? Of course, that's it, because you know all the coefficients here. You use these coefficients, they plug in here, you get the difference equation. And when you have this one, you have the frequency response, which is a summation of bk e to the negative j omega over summation k run from 0 p, and here's k run from 0 to q. Here's a k z e to the negative j omega. So you can also have the frequency response. So when you have when you have difference equation, you can have transfer function and the frequency response. Just one step. You just write it down. You don't need to perform the Fourier transform or perform the Z transform to get it. You can have this one. Alright. What else? If we go inside for the details of this part, we need more time for these materials, as I stated here in the whole section 2.2. The whole section, totally 18 pages. Not 18. From page 8 to page 18, so 10 pages. If you want, you can read this part to know all the details. Of course, if you're still familiar with them, I know some of you guys just took 317 like last semester, so you should remember everything here, right? Then that will be fine. If you think you are not so clearly, you forgot something, then you can read this part for all the details. Now today I just give you a brief review of this part, okay? And later when we need the information from this part, we can go back to see what it is. Alright, and I will also give you some exercise problems related with this part, and which will be part of the quiz 1 problems. Some of the problems in the exercise problems will be in the quiz 1. Which quiz 1 will be in the 3rd week. Alright. What else for today? That's all for today. So thank you to attend the class. This is an online class, and see you next time. See you on Friday. Bye bye.